In this video, I'm going to show that any sequence that's a Cauchy sequence is also bounded. So first remember that a sequence AN is a Cauchy sequence if for all epsilon greater than 0, there exists a natural number m such that for all j, k greater than or equal to m, the absolute value of aj minus ak is less than epsilon. So this is saying that if you go far enough into the sequence, the terms will be as close together as you like, since you can choose epsilon to be anything. So let's take advantage of that fact, and let's set epsilon equal to 1. This means, because the sequence is Cauchy, that there exists a number m prime such that for all c, d greater than or equal to m prime, ac minus ad is less than 1. So that means that after the m prime term, all of these terms in the sequence A are going to be within 1 of each other. So now let's call the value of the m prime term capital B. So am prime equals B. Now we know that after am prime, the terms are never going to be further away than 1 from am prime. So this means that they can't be more than b plus 1. So now we're going to write for all ak such that k is greater than or equal to m prime, a sub k is less than b plus 1. So now we have an upper bound on all of the terms that come after the m prime term. So all we have to do is look at all the terms that come before that. So we'll look at a1, a2, a3, all the way up to am prime minus 1. And we're going to say, what's the biggest out of all of those? And we'll call that capital F, capital F. So now we can find this maximum because this is a finite number of terms. We can't do that with an infinite number of terms, but we can do that with a finite number of terms. So we have the biggest number out of the finite terms up to m prime, which is f, and then we have the biggest number that it could possibly achieve after the m prime term, and that's b plus 1. So now take the bigger of those two, and call it S. And now we have an upper bound for the whole sequence. We know that for all an, or for all n, an is less than or equal to S. So this is showing that the sequence has an upper bound, and you can very easily, either by doing another proof and looking for a minimum and doing b minus 1, or simply by doing it all in one shot with absolute values, show that it's bounded from below too. In this video, I'm just going to show that it's bounded from above, and then assume that by looking at this, if you really understand it, you can see why it's bounded from below, and you can show that. So now I want to draw a picture of what this really means. So say these red lines are 1 apart from each other. And then let's let the blue line be the terms in our Cauchy sequence. So we know that a Cauchy sequence can do anything in the beginning. It's bouncing around, but then it has to be, all of the terms have to be within 1 of each other after a point, which we called that point, or we called that term the m prime term. So after am prime, all of the terms are within 1 of each other. So we look at the biggest value that an could possibly achieve after am prime, and that's this top red line. And then we also look at the biggest value that the Cauchy sequence achieves before getting there. So in my picture, it looks like this is probably it. And we look at the bigger of those two, and in this case, it's this one. So that is going to be our upper bound S. We could think of another situation where when the Cauchy sequence was bouncing around, it didn't go above that number. It just hung out below it. And then we know that in that case, more like this, in that case, this is going to be the upper bound, this top red line, because all of the terms in the sequence are below that one.